Hey everyone, welcome back to the Deep Dive. We're diving into something that I think is incredibly relevant to pretty much everyone who's listening, especially today when we're just bombarded with information from all sides. We're going to be exploring how we learn with multimedia. So, how do our brains actually make sense of all the text, images, and audio that we're constantly exposed to?
It's a really fascinating area and one that has huge implications for how we design learning materials, how we approach learning ourselves, just in general,
Yeah.
making the most of how our brains are wired to process this kind of mixed input.
Right, exactly. And I think, for our listeners who are really interested in learning effectively and efficiently, which I imagine is most of you understanding how these cognitive processes work can give you a real advantage. It's about learning smarter, not just harder.
Absolutely. Cutting through the noise and figuring out what actually works.
So to really guide this deep dive, we're going to be looking at a really interesting academic paper. It's called Attention, Working Memory, and Long-Term Memory in Multimedia Learning, an integrated perspective based on process models of working memory, and it was published in 2014 by, let me make sure I get the names right, Schweppe and Rummer.
Yeah, that's the one. It's a great paper. It takes a fresh perspective on how we think about working memory and attention in the context of multimedia learning.
And, a lot of the traditional thinking about how we learn with multimedia has been influenced by these sort of big theories, the cognitive theory of multimedia learning, or CTML, and cognitive load theory, CLT. And these often present this view of memory as having kind of distinct areas, like a separate working memory, which is kind of like our mental scratch pad, that temporary space where we hold and manipulate information. And then you have long-term memory, which is that vast storehouse of knowledge and experience that we've built up over time.
Yeah. And the traditional idea, often stemming from models like Baddeley's very influential multi-component model, was that this working memory system had a really limited capacity, right? You could only hold so much information there at once. So it's sort of doing the heavy lifting, the active processing, but it's really constrained.
Right, like a bottleneck.
Mm.
And that's where our featured paper really takes a different approach. Schwepp and Rummer are champions of the embedded processes model of working memory, which is largely based on the work of Nelson Cowan.
And the really interesting thing about this embedded view is that it doesn't see working memory as a separate system. Instead, it suggests that working memory is essentially the activated part of your long-term memory.
Okay, so it's not like a separate box in the brain.
Not exactly. Think of it this way. Imagine your long-term memory is like a vast library filled with books representing all the knowledge you've acquired. Now, working memory, according to this view, is like the books you've pulled off the shelves and have open on your desk, ready to be read and used. They're still part of the library, but they're in this state of heightened accessibility.
That's a really helpful analogy. So it's not about where the information is stored, but about how accessible it is at that moment.
Exactly. And within this activated portion of long-term memory, Cowan's model suggests there's this even more focused spotlight, which is called the focus of attention.
So that's like the book you're actually reading right now, the one you're really focused on.
Exactly. It's the information that's most readily available to your conscious awareness. But here's the interesting part. Cowan suggests that even information that's activated but not quite in that bright spotlight, so maybe like the books that are open on your desk but you're not actively reading them, can still be retrieved fairly easily. And he even proposes that an item that's not currently activated could still be considered part of working memory if there are strong cues pointing to it.
So it's like having a bookmark in a book that's still on the shelf, where to find it quickly if you need it.
Right. So the key insight here is that a lot of what we consider working memory might not actually be something we're consciously aware of at any given moment.
That's a really different way to think about it than just a limited capacity holding area.
Right.
So where does this embedded processes model leave us in terms of understanding how we actually learn with multimedia?
Well, I think it brings some really crucial advantages. For one, it places much stronger emphasis on long-term memory right from the start. It recognizes that what we already know plays a huge role in how we process and make sense of new information, even in the moment.
So it's not just about taking in new information, but about how that new information connects with our existing knowledge base.
Exactly. And secondly, I think it gives us a really powerful way to think about multimedia learning through the lens of attention. This viewpoint allows us to re-examine and reinterpret some of the well-established multimedia learning effects we've seen and potentially even predict new ones.
Okay, so let's dig into some of those key differences between this embedded view and the more traditional separate systems view of working memory.
Yeah.
You used that great analogy earlier about the library and the books on the desk. Can you maybe expand on that a bit more?
Sure. So if we think back to that computer analogy, the traditional view is kind of like saying that your computer's RAM, that's the random access memory, which is a bit like working memory in the traditional view, is totally separate from your hard drive, which is like your long-term memory. The RAM is small and fast, but it's fundamentally different from where everything is permanently stored.
So it's like you have these two separate places, and information has to be transferred back and forth between them.
Right. But the embedded processes view is more like saying that working memory is simply the files and applications you currently have open and are actively using on your computer. It's not that they're in some special RAM zone, they're just the parts of your hard drive that are in a highly accessible state because you're actively working with them.
So it's about the state of the information, not its location.
Exactly. And this shift has some important implications.
Okay, so let's walk through Callan's embedded processes model a bit more systematically. How does it actually work? What are the main components?
Well, the starting point is that we have sensory memory, which is that very brief, almost fleeting registration of sensory input. And then we have long-term memory, which is our vast knowledge store. And working memory, rather than being a separate structure, is viewed as a state within long-term memory, a state of heightened activation. It's essentially cognitive processes that retain information in an unusually accessible state.
So when we encounter something new, what happens?
When you encounter something, it triggers activity in your long-term memory related to that thing. It's like a ripple effect spreading out from the point of contact. And the more attention you pay to something, or the more attention grabbing it is, the more features of that thing get activated in your long-term memory. And this includes not just its physical characteristics, but also its meaning and its relationship to other things you know.
So attention really is key here.
Yeah.
And we talked about that focus of attention, that spotlight within working memory. What exactly is happening in that spotlight?
The focus of attention is like the most intense part of that ripple of activation. It's the information that's most readily accessible and consciously available. But remember, even things outside of that spotlight can still be part of working memory if they're activated or if there are strong cues pointing to them. And Cowan suggests that this focus of attention has a very limited capacity. We can only hold about 4 unconnected items or chunks of information there at once.
That magical number 4 comes up again. And you mentioned chunks earlier. Can you explain what a chunk is?
A chunk is essentially a meaningful unit of information. It could be a single word, a familiar phrase, a visual element, or even a complex idea, as long as it's something you can treat as a single unit in your mind. And the size of a chunk can vary a lot depending on your prior knowledge and experience.
So someone with more expertise in a particular area might be able to form larger chunks, allowing them to hold more information in their focus of attention.
Exactly. That's a key advantage of expertise.
Okay, so we've talked about how information gets activated in long-term memory and how attention influences that process. But what about forgetting? If working memory isn't a separate limited capacity store, how does forgetting work in this model?
Well, in the embedded processes model, forgetting primarily happens in a couple of ways. First, there's a time limit on how long information can stay highly activated in long-term memory. This involves both decay, where the activation simply fades over time, and interference, where other similar information gets in the way.
So it's like if you meet someone new at a party and they tell you their name, but then you get distracted by other conversations. If you don't make a conscious effort to remember the name, it's likely to fade away, and other names you hear might interfere with your ability to recall it.
Exactly. And the second reason for forgetting is that limited capacity of the focus of attention. Remember, we can only hold about 4 chunks in that spotlight at once. So if something gets pushed out of that focus, it becomes less accessible, and if it's not reactivated, it might eventually become so weakly activated that it's essentially forgotten.
So it's not about running out of space, but about the information becoming less and less accessible over time.
Right.
Okay, so if information can fade or get pushed out of our attentional focus, how do we keep important things active and accessible? How does maintenance happen in this model?
Maintenance, in Cowan's model, is primarily the job of the central executive. It's those mental processes that keep information active and refreshed in your focus of attention. It's like mentally rehearsing something you want to remember, or actively thinking about it and making connections to other things you know. And what's crucial here is that these maintenance processes are domain general. They're not specific to just words or just images. They apply to any type of information.
So it's like that inner voice we all have that can repeat information, ask ourselves questions about it, or try to relate it to something we already know.
Exactly. It's that active engagement with the information that keeps it alive in our minds. but it does require effort. It's not a passive process.
And this is where the idea of cognitive load comes in, right?
Yeah.
That mental effort and those resources we have available for these processes.
Absolutely. And this is where the embedded processes model offers a really useful way to understand how those limited resources are used and how they can become overloaded.
Okay, so let's tie this back to some of the big theories of multimedia learning we talked about earlier. How does this embedded processes model change how we understand the cognitive theory of multimedia learning, or CTML?
Well, it gives us a really interesting reinterpretation of those key stages that the CTML talks about: selecting, organizing, and integrating information. From this new perspective, selecting becomes more about activating relevant information in long-term memory and then directing our attention to it. And this can happen either because something grabs our attention automatically or because we consciously choose to focus on it.
So it's not just about picking out important information from the environment, but about activating the relevant knowledge we already have.
Right. And then as for organizing and integrating, those processes essentially become part of the single process of encoding information into long-term memory. Because ultimately, all new learning involves connecting with what we already know.
So encoding is inherently an integrative process.
Exactly. It's about building those connections.
Okay, so the big shifts are in how we understand working memory itself and the role of attention in learning.
Precisely. And the embedded processes model really highlights the crucial distinction between involuntary attention, which is that automatic stimulus-driven response to things that stand out, and voluntary attention, which is when we consciously direct our focus using those central executive resources.
So things like a sudden loud noise or a flash of bright light would grab our involuntary attention, while trying to solve a complex math problem or follow a detailed set of instructions would require voluntary attention.
Exactly. And the paper argues that to really make the CTML more comprehensive and accurate, we need to explicitly incorporate this idea of a central executive that guides our voluntary attention.
Because learning often requires us to focus on things that aren't inherently attention-grabbing.
Right. We have to actively direct our attention to the things that are most important for learning, even if they're not the most exciting or stimulating things in the environment.
Okay, so what about cognitive load theory, or CLT? How does this embedded processes model help us understand concepts like intrinsic and extraneous cognitive load?
I think it gives us a much more refined understanding of how these different types of cognitive load relate to the limited capacity of our attentional focus.
So let's start with intrinsic load, that load that comes from the inherent difficulty of the material itself. How does this new perspective on working memory and attention help us understand that?
Well, the traditional view of intrinsic load is that it's about how much information needs to be processed simultaneously in working memory to understand something. But the embedded processes model highlights that the real bottleneck is the capacity of our attentional focus, which is limited to about 4 chunks. So if learning requires us to try to hold more than 4 unconnected elements in mind at the same time, it's going to exceed our capacity for effective encoding.
So if a learning task is too complex, it's not just that we don't have enough space in working memory, it's that we can't effectively focus our attention on all the necessary elements at once.
Exactly. And this is where the idea of chunking becomes really important. If we can group information together into meaningful chunks, we can effectively reduce the number of elements we need to hold in our focus of attention, which can make learning more efficient.
And this also explains why expertise can be so beneficial, right? Because experts are better at chunking information based on their prior knowledge.
Absolutely. Their long-term memory is organized in a way that allows them to see connections and group information into larger, more meaningful units.
Okay, what about extraneous cognitive load? The load that's imposed by poorly designed instructional materials or a distracting learning environment. How does the embedded processes model reinterpret that?
The embedded processes model suggests that extraneous cognitive load is essentially anything that prevents relevant information from getting into or staying within our focus of attention. And it helps us distinguish between 2 key ways this can happen.
So it's not just about information overload, it's about how our attention is managed.
Exactly. So the first way extraneous load can arise is through involuntary attention capture. This is when irrelevant stimuli in the environment grab our attention, pulling it away from the things we should be focusing on.
Like those annoying pop-up ads that keep appearing while you're trying to read something online.
Exactly. Or those flashy animations that are visually interesting but don't actually contribute to the learning. These things can hijack our attention even if we don't want them to.
So the first lesson for designers of learning materials is to avoid including things that are likely to distract learners from the core content.
Absolutely. Don't make learners fight against their own involuntary attention. The second way extraneous load can occur is through inefficient voluntary allocation of attention. This is when the design of the materials makes it difficult to figure out what to focus on, or when it forces us to engage in mentally demanding but ultimately irrelevant processes.
So it's not just about distractions, it's also about making the learning process as smooth and efficient as possible.
Right. For example, if a diagram is overly complex or poorly labeled, learners might have to spend a lot of mental effort just trying to figure out what they're looking at, which leaves less mental capacity for actually understanding the content.
So it's about designing materials that guide attention effectively and minimize the need for unnecessary mental effort.
Exactly. Make it clear what's important and make it easy to find and process that information.
This has been a really insightful look at how the embedded processes model gives us a new way to think about these fundamental concepts of cognitive load. Now let's dive into how this model helps us understand some of the classic multimedia learning effects. Let's start with the split attention effect. Why is it beneficial to present related verbal and visual information closer in time and space?
The embedded processes model suggests that for us to truly integrate information from different sources, like text and visuals, those pieces of information need to be in our focus of attention at the same time, or at least very close together in time. If the information is separated, either temporally or spatially, it requires extra mental effort to make those connections. We have to actively rehearse the information or visually search for the connections, and that uses up those limited central executive resources.
So it's like trying to assemble a piece of furniture with the instructions on one side of the room and the parts on the other side. You have to keep going back and forth, and it's easy to forget what you were doing or to lose track of a piece.
Exactly. It's inefficient and mentally taxing. And if we're having to use up those resources just to manage the information, it leaves less capacity for actually understanding it and making those deeper connections.
So the takeaway for designers is to keep related information together, both in time and in space. Don't make learners work harder than they have to.
Exactly. Minimize that split attention effect.
And this model also offers some interesting insights into variations of the split attention effect, right? Like that prediction about spoken and written text when there's a lot of visual searching involved.
Yeah, that's an interesting one. So typically, we find that people learn better when information is presented as spoken text rather than written text, especially when it's paired with visuals. But the embedded processes model suggests that if there's a lot of visual searching required to connect the spoken text to the visual, that advantage of spoken text might disappear.
But because the act of searching takes up so much attentional capacity that it cancels out the benefit of the simultaneous auditory input.
Exactly. And there's research that supports this prediction. Zheng and colleagues found that when learners had to search for specific information within a complex diagram while listening to spoken instructions, they didn't perform any better than learners who had the instructions presented as on-screen text.
So even though the spoken text freed up their visual channel, the demands of the search task overwhelmed their attentional capacity anyway.
Exactly. And another thing to keep in mind is that if there are really noticeable but irrelevant things in the visuals, those can also grab that involuntary attention and make it harder to focus on the important information.
So it's not just about the placement of the information, but also about the visual design itself.
Absolutely. Minimize distractions, highlight the important stuff, and make it clear how the different pieces of information connect.
Okay, let's move on to the modality effect. This is the finding that we often learn better when text is presented as speech rather than on-screen text, especially when it's paired with visuals. How does the embedded processes model explain this?
Well, the traditional explanation for the modality effect often relies on this idea of dual channels in working memory, one for verbal information and one for visual information, each with its own limited capacity. But as we've discussed, the embedded processes model challenges this idea of fundamentally separate capacity-limited channels for different senses. It suggests that it's our overall attentional capacity, our central mental workspace, that's limited, regardless of the sensory modality of the information.
So just presenting information through two different senses doesn't automatically get around that bottleneck?
Exactly. And this raises the question of why we do see a modality effect in many cases. The paper offers a few potential explanations from the perspective of the embedded processes model. One is that it might be a specific instance of the split attention effect. Remember, our eyes can't focus on both written text and a complex image at the same time. So when both the text and the visual are presented visually, it forces a kind of back and forth processing, which can be mentally demanding.
But when the text is presented auditorily, we can process it while looking at the visual, which is more efficient.
Exactly. It reduces the need for that attentional switching. Another potential explanation is related to how long information lingers in our sensory memory. Auditory information tends to persist a bit longer than visual information, which might be particularly helpful for processing short verbal segments that need to be integrated with a visual.
So it gives a little bit more time to make that connection before the information fades away.
Right. And there's research that supports this idea. Some studies have found a modality effect with short texts, but not with longer ones, suggesting that this longer-lasting auditory trace might be particularly beneficial for integrating smaller chunks of verbal information.
So the modality effect might be less about separate working memory stores and more about the specific ways our senses and attention interact with the timing of information processing.
I think that's a more accurate way to think about it.
Okay, let's move on to another classic multimedia learning effect, the seductive details effect. This is the finding that adding interesting but irrelevant information to learning materials can sometimes actually hinder learning. How does the embedded processes model account for that?
The embedded processes model offers a pretty straightforward explanation for this effect. Because seductive details are interesting or novel, they tend to capture our attention, either involuntarily because they stand out, or voluntarily if we're not sure what's important or if we're not completely focused on the learning task. And once these irrelevant details enter our focus of attention, they take up valuable space that's needed for processing the essential learning materials.
It's like having too many tabs open on your web browser. It slows down the whole system.
Exactly. It creates mental clutter that interferes with processing.
And this model also helps us understand when seductive details might be more or less harmful, right?
Absolutely. The model predicts that the seductive details effect should be stronger for learners who don't have a lot of prior knowledge in the area.
Because they might have a harder time distinguishing between what's important and what's just interesting.
Exactly. They're more likely to get sidetracked by those seductive details. Similarly, learners who aren't very motivated to learn the specific material might be more drawn to the engaging but irrelevant content. And of course, the more novel and attention-grabbing the seductive details are, the more likely they are to pull our focus away from the important stuff.
So it's not just about avoiding irrelevant information altogether,
Ugh.
but about being mindful of how that information is presented and who the audience is.
Exactly. Think about your learners, their prior knowledge, and their motivation levels.
Okay, what about the signaling effect? This is the idea that cues, like arrows or highlighting, can actually improve learning. How does the embedded processes model explain that?
From the perspective of the embedded processes model, signaling works because it guides learners' attention to the most important information. And when we attend to something, we activate more of its features in long-term memory, leading to deeper processing and stronger storage. So cues essentially make it more likely that the crucial aspects of the learning material will enter that limited focus of attention.
So it's like a signpost pointing us in the right direction.
Exactly. It reduces the mental effort required to find the important stuff. And the model also gives us some insights into when signaling is likely to be most effective. Remember, Cowan's model distinguishes between effortless involuntary attention and more effortful voluntary attention.
So signaling is most helpful when it reduces the need for that effortful voluntary attention.
Precisely. So signaling should be most beneficial when the important information might otherwise be easily missed or overlooked. For example, if there are subtle but critical changes in an animation, signaling can help draw attention to those changes.
It's like a flashing neon sign saying, hey, pay attention to this.
Right. But on the other hand, if the important information is already really obvious, adding signals might not provide much additional benefit. And if we overuse signals, they can actually become distracting because we become habituated to them.
It's like the boy who cried wolf. If everything is signaled as important, then nothing seems important.
Exactly. So use signals strategically and sparingly, and make sure they're really directing attention to the most critical information.
Okay, let's move on to the redundancy effect. This is the idea that presenting the same information in multiple formats, like both spoken and written text, can sometimes hinder learning. How does the embedded processes model explain that?
The traditional explanation often focuses on the idea that processing redundant information overloads working memory. But the embedded processes model offers a slightly different perspective. It suggests that if learners don't realize the information is redundant, or if they find it difficult to ignore one of the sources, then those redundant elements can still occupy space in the focus of attention. This reduces the mental capacity available for processing new information and making connections.
So it's not just about the amount of information, but about how that information is managed within our attentional focus.
Exactly. And this model also helps explain why, in some cases, presenting redundant information can actually be beneficial. If learners are able to effectively chunk the information from the different sources, treating it as a single unit in their focus of attention, then the redundancy might not be problematic.
Because they're essentially ignoring the redundancy and focusing on the underlying meaning.
Exactly. And this is where signaling can come into play again. If key points are highlighted within redundant text, it can actually improve learning because it acts as a form of signaling, helping learners to focus on the most important information.
So it's not just about avoiding redundancy, but about managing it effectively and using it strategically.
Right. Think about how you can help learners chunk information and focus on the key takeaways.
Okay, finally, let's talk about the expertise reversal effect. This is the finding that instructional strategies that are helpful for beginners can sometimes be less effective or even harmful for learners who already have a lot of knowledge. How does the embedded processes model help us understand this?
The embedded processes model suggests that this effect might be related to the fact that learners with more prior knowledge have a better organized long-term memory, which allows them to chunk information more efficiently and rely more on activating their existing knowledge. So instructional guidance that's designed to reduce the number of elements in the focus of attention might be less necessary for them. In fact, it might even feel redundant or overly simplistic.
So they're essentially able to bypass some of the cognitive load that beginners experience because they can draw on their existing knowledge to make connections and fill in the gaps.
Exactly. They're working with larger, more integrated chunks of information. But the paper also points out that the expertise reversal effect is likely a complex phenomenon. It's not just about working memory capacity. Learners with high prior knowledge might also find overly simplistic or highly guided materials boring, or they might find that the instructional content conflicts with their existing understanding, which can lead to less engagement and even resistance to the new information.
So it's about finding the right balance between providing support and allowing learners to leverage their expertise.
Absolutely. And this is where knowing your audience is crucial. Consider their prior knowledge, their goals, and their learning preferences.
This has been a really insightful exploration of how the embedded processes model gives us a new way to think about multimedia learning. One final area the paper touches on is individual differences in working memory capacity. How does this model, particularly the controlled attention theory, help us understand how people with different working memory capacities might interact with multimedia learning materials?
The controlled attention theory essentially views working memory capacity not just as a limit on how much we can hold in mind, but more as our ability to control and direct our attention, to suppress distractions, and to keep relevant information active even in the face of interference.
So it's not just about storage capacity, but about the ability to manage that capacity effectively.
Exactly. And from this viewpoint, learners with lower working memory capacity, meaning they have less control over their attention, should be more susceptible to things like seductive details and split attention effects. They might struggle to keep their focus on the essential information when there are distractions present, and they might find it more difficult to process information from multiple sources simultaneously.
So they might need more support in terms of reducing distractions and managing the complexity of the information.
Right. And there's some research that supports this idea. For example, studies have shown that the seductive details effect is often stronger for individuals with lower working memory capacity. And although more research is needed to fully understand the interplay between working memory capacity and multimedia learning, this focus on attentional control provides a really promising framework for understanding why different learners might experience the same materials in different ways.
That's a really crucial point. It's not just about designing one-size-fits-all materials, but about recognizing that different learners have different needs and strengths.
Absolutely. And understanding those differences can help us create more effective and inclusive learning experiences.
This has been a truly fascinating deep dive into the embedded processes model and its implications for how we learn with multimedia. So for you, our listener, what's the biggest takeaway from all of this? What should you be thinking about as you go about your own learning or as you design learning experiences for others?
I think the key takeaway is that this model gives us a much more integrated and nuanced understanding of how our minds work when we're learning with multimedia. It highlights the dynamic interplay between our attention, the activated parts of our long-term memory, and that limited focus of our conscious processing. It's not about separate boxes in our brain. It's about how we manage our mental resources and how effectively we direct our attention to the things that matter most.
And how can this understanding actually help people become more effective learners?
It can help you be more strategic in how you approach learning. For example, by understanding how easily you can get distracted by irrelevant information, you can be more proactive in creating a learning environment that minimizes distractions. You can also use this knowledge to evaluate learning materials more critically. If you're finding something confusing or difficult, think about whether it might be due to poorly managed cognitive load, like too much information presented at once, or unclear signaling of what's important.
So it's about becoming more aware of your own cognitive processes and using that awareness to your advantage.
Exactly. And it's also about recognizing that everyone learns differently and that there's no single right way to design learning materials.
So here's a final thought for you, our listener, to ponder. Given the limited capacity of your attentional focus, what's one thing you could change about your learning environment or your learning habits to reduce overload and maximize your understanding?
And remember, we've only just scratched the surface of this incredibly rich and complex topic. If you found this discussion intriguing, we encourage you to explore the research we've mentioned, particularly that 2014 paper by Schwepp and Rummer, Attention, Working Memory, and Long-Term Memory in Multimedia Learning, which can be found in the journal Educational Psychology Review. There's so much more to discover about the fascinating world of how our brains learn.
Thank you for joining us for this deep dive. Until next time, keep those minds engaged and keep learning.